So,
Thank
hello,
you.
everybody.
Thank you for coming. Undefined behavior. I'm Barbara.
I'm Ansel.
English
we got that
is
the right way around this time?
Yeah, we did. We usually mess that up. We're from the San Francisco Bay Area, coming here from the United States. Thanks to Odin and the company for inviting us. This is basically what we're going to do. This talk is really about an hour and 15. We're going to go insanely fast. We're a little bit animated. If our English is messed up, please raise your hand. If you have questions, we love comments from the audience. How many people have heard of Copper Spice? Cool. Cool. Well, we are the founders of Copper Spice. We wanted to tell you very briefly who we are. Copper Spice is a fork of the Qt project. And yes, it's a fork of the entire Qt project that we did a couple years ago. And we are the maintainers. We have contributors here to our library. It is a set of cross-platform C++ libraries. If you're not familiar with it and you want to know more, we'll tell you how to find out and you can chat with us. In the process of doing Copper Spice, we tried to use Doxygen to document it, and we have quite a few templates, and it puked. So we ended up forking Doxygen and wrote DoxyPress. And laughter's okay. People laugh at us. And DoxyPress took us a year detour. If you are documenting, move to DoxyPress. If you're not documenting, start documenting. And use DoxyPress. It's quite accurate. We can tell you more about that later.
Another thing we've done along the way is extracted certain libraries from Copper Spice. So CS-string and CS-signal are standalone libraries that provide a Unicode-aware string library, a drop-in replacement for std string, and CS-signal is a thread-aware signal slot delivery library.
libguarded is another library that Ansel did more of than I did, although I broke it quite a lot. We're doing a talk this afternoon that's been added to the schedule at 2 o'clock. We're going to actually do a 2-hour compressed 50-minute talk on libguarded. We're going to try. Our credentials. We use C++. That's good.
We use modern
C++.
Entirely.
And that's one of the things with Copper Spice in any of our libraries. We're currently using 14. Once we get back to the States in April, we're here a couple weeks, we're moving to 17 as our lowest common denominator. But that's what separates us from Qt and the Doxygen DoxyPress, is that we believe in using modern C++ idioms.
Let's actually talk about undefined behavior now.
Cool.
So there's a lot of people that have given talks about undefined behavior, and they always talk about it from the standpoint of a compiler developer. And they're really interesting, and you should definitely watch them. But will they teach you what you need to know as a regular end user of the compiler to write good code? Not necessarily. They're really fascinating, and you could do a whole master's thesis on it. But this isn't going to help you write code that works.
We're making the assumption that most of you are not compiler designers, and you actually want to know how to tell if your code has undefined behavior and why it shouldn't. So this is our approach, is from a programming standpoint.
There's also a fair number of myths and misunderstandings about undefined behavior, and these are surprisingly common. I've seen people say, oh, well, I just don't put undefined behavior in my programs because it's fairly easy to see. And so I just don't do that. And there are a lot of people who say, wait, what? The compiler won't tell me when I have undefined behavior? No.
It can't.
Sometimes,
Not all the
occasionally,
time.
a few things it will catch. But no, in general, it can't.
And we are going to talk about a little bit about how to debug. Our main focus is how to recognize what is undefined behavior. One of the things we do want to mention is we need a lot of definitions before we get to the really cool stuff in this talk. And it takes a lot to get to the definitions. And then it gets complicated really fast.
So we need to form some mathematically precise definitions of what we're talking about. So defined behavior. This has a specific meaning in the standard. It says, this is code which has a single prescribed Meaning, if you initialize sum to 5 plus 2 and you don't get the result 7, your compiler is broken. It's not following the standard. This printf statement doesn't say, welcome to this lovely country, then your compiler is broken. Then there's implementation-defined behavior, which means it's code that has multiple possible meanings according to the standard. The compiler has to pick one, use it consistently, and document its choice. And so here's an example. We're saying, on my platform, is the size of an int less than the size of a long? This is a perfectly reasonable question to ask. The answer is either true or false, but you don't know which one it is until you know what platform you're on and what your compiler is doing with these data types. Any questions so far?
And then there's unspecified behavior. And this is code which can have several different meanings. This line of code ABC equals ABC, it's a silly line of code, but what is it actually comparing? Is it comparing strings, or is it actually comparing the address of something?
This is comparing the address of two string literals, which are equal. And the question is, did the compiler put those both in the same place, or are they two separate string literals? And the answer, according to the standard, is unspecified, which means this if must either be true or false, but there's no predicting which one it is. It could change from one run to the other. It could change when you change optimization flags. You have no guarantees about which one will be chosen. But it is guaranteed to be one or the other.
And then there's undefined behavior, and it has no meaning. What gets complicated is defining something that has no meaning. These are just some really brief examples because they're really obvious, like accessing an object after it's been destroyed. If you do that, you don't know what you're going to get. So this is a very small list, but it helps us to define the difference between these 4 different categories. Yes? From compile to compile.
From compile to compile, or from run to run. Unspecified. It is guaranteed to be either true or false, but you can't reason about when it will be true and when it will be false. There's no guarantee on that level.
So the compiler is not consistent.
Right.
True, it doesn't need to be. And these are actual definitions based on the C++ standard.
Mm-hmm. When the standard says something is unspecified, this is what it means.
So what's not part of the standard is an error. And these are valid errors. If you're writing code and you need somebody to find a file or open up a port or do something, you should check, make sure the file's there, make sure the port is open. The standard doesn't say anything about this because these are valid things that you need to be responsible for checking. It would be nice to make sure the file you need is actually there.
The standard also doesn't talk about intended behavior. The standard doesn't actually distinguish between your program did what you wanted and your program encountered some error and handled it. They're both just proceeding according to the rules of the standard.
So if you're running our doxypress program and it documents and it just works, the standard doesn't actually say anything about that, which is actually very interesting that it doesn't say, hey, your intended behavior worked. No gold stars come up and tell you, yay. So what is undefined behavior? It is the result of attempting to execute source code that is not defined in the standard.
And it's our responsibility as programmers to never, ever write code which has undefined behavior. Because there's actually a definition in the standard. A correct program must be free of undefined behavior. Which means, by definition, if your program has any undefined behavior, it is not correct. It does not meet any specification. Because the entire program contains undefined behavior. The standard doesn't say what will actually happen when you execute it at that point.
So here's an example that I find kind of interesting. We do a lot of things in relationship to food. If you have a chocolate cake recipe and it says you can use walnuts or not, whatever you do is fine. I don't like walnuts, leave it out of my cake, it's fine. But if the recipe calls for a teaspoon of salt, and you put in a cup of salt, I guarantee you it is going to be an atrocious, awful cake.
I probably should have translated this. That's about 5 milliliters versus 500 milliliters, roughly.
Oh, yes, we should have done that, yes. But the truth is, and the reason why we brought up this example, you're saying, well, the salt is undefined. No, your entire cake is undefined. It may work, it may not cook, it may fall. It is undefined.
Now, if you happen to be a vegan, like I grew up, you might replace the milk with soy milk.
I'm sorry.
It's very possible this will work. You may get a cake. It's still undefined behavior because you're outside of what the recipe said you should do. So you may get a result that seems like a cake, but it's not the cake that the recipe promised. It's really important to understand this because if you don't know how dangerous undefined behavior is, you might not realize how much trouble you're in. We as programmers tend to ignore things that don't happen often. This is a really bad idea if the thing that rarely happens is a result of undefined behavior. And most of the time the code works. This is also really important if you're doing anything which is either safety critical or a security boundary, like a web server. You need to be sure that bad input into your process doesn't cause undefined behavior. I mean, most security holes are a result of being able to provoke undefined behavior in the targeted process.
So we had a place that we needed to design some metadata. And if you were at our lightning talk last night, this was the metadata registration. And as we mentioned last night, over much beer, version 1 looked like it worked beautifully. And then we had some Clang developers look at it. And they said, well, this is nice, but thank you. You just pointed out a flaw in Clang. We need to optimize Clang better because you used undefined behavior from the standard in the sense that what we were doing was basically illegal. And in 6 months or a year, your program's going to crash. Fix it.
So what do you do when the implementers of Clang say, your code is not valid and has undefined behavior? You immediately go and rewrite it.
And version 3 is what we showed a little bit of our compile time counter. It uses a lot of really cool stuff, but now it's been blessed. And they have said, no, you're not doing any violation. This is a good thing. Because again, if this one little piece of copper spice had undefined behavior, it would have meant all of our library work was undefined.
So let's look at a list. This is not a complete list. And as you'll see, you actually can't form a complete list. But these are sort of the greatest hits of undefined behavior. These are the ones that come up over and over and over again, like dereferencing a null pointer. Who here has never dereferenced a null pointer?
Cool.
Very impressive.
Very impressive. He doesn't write code. I'm just kidding.
Working in...
You don't use pointers.
Fair enough.
See, that was my point.
Yep.
Yeah.
Accessing an element of an array that's out of bounds. These are things which to most practicing programmers are obvious. You shouldn't do this. The reason you shouldn't do this is because they're undefined behavior. Is there a question?
Unspecified, isn't it?
No, it is undefined.
But that's an excellent question.
If it's unspecified, your integer representation is not proper representation. You can act as an
That is C11. That is not C++, I believe.
That might be the case. That might be C, yeah.
Somebody. Okay. Behavior. Yeah.
Yeah.
It's also not very readable code. So even if it felt unspecified, initialize your variables.
It is a good idea.
It is a good idea, but it would be undefined. But a good question.
I'm fairly sure that's actually a distinction between C and C++.
Yeah.
So
this is the really cool part where I get to use my English. Undefined behavior is not an error. I like S fine, so we came up with U bine. So that's what this is U bine. Undefined behavior is not an error. An error is an error. Undefined behavior is garbage.
The reason why this is a very important distinction to make is an error is something you can handle. It's a condition that happens at runtime or potentially at compile time. We've all written plenty of compile errors, I'm sure. But you can do something about it. You can't do anything about undefined behavior. Once it has occurred, you're too late because the program is in a completely unknown state and you have no way of dealing with it. So you have to prevent it rather than handle it. And so, we have things that we deal with that result in runtime errors or compile time errors. These are all things you can actually take some action to address. And undefined behavior just blows up your program.
So we've come up with EC, the compiler of the future. And I am an evil compiler.
And I am a very efficient compiler.
And I'm going to optimize your code, and I'm going to get rid of everything that is undefined if I have to take out the whole thing.
And I want to be efficient, so I'm going to optimize your code and take out everything that's undefined behavior because I know you didn't mean to write that.
This is where the future is going. The future of compilers are both evil and kind of efficient.
Because it's really the same thing.
Yes.
And sometimes we throw away all your undefined behavior. Sometimes we reorder code based on our knowledge of what your code means.
Pretty rare.
So some of the things we're about to show you won't actually cause problems because they work in the way you think they should. As you turn on optimization, the compiler gets much more aggressive about reordering and rearranging your code. It actually looks at the semantic meaning of everything you're doing and tries to find efficiency there. Which means if your code works when optimization is off and it breaks when you turn on optimization, the chances are it's because you have undefined behavior somewhere.
So a quick recap just to get these four terms back out. Defined behavior, implementation defined behavior, unspecified, and undefined. So let's take a look at another example. How many people have forgotten the return type?
Return statement?
Return statement.
Yeah.
See, it happens. We did it too when we were staring at the code. It's very easy here to see we've missed the return type. It's not so easy when your code is just flaky. One of the things that happens at the compiler level is, who knows? It's undefined behavior.
Who cares? It's
But what was
undefined
actually happening to us is it was just going through, and if you think about the assembly code, it just went until it found a return statement. Way down, not even in the same function or method.
It would just continue to the next function, whatever that is.
There are ways of checking for this with some switches when you compile. We now have them turned on. We did not at the time. So there are some compiler warnings you can get. This is really at the compiler level. We wanted to show one thing for compilers.
This was a fun one to debug. So this is some code we inherited from a previous developer. And it was using the QString class. And for those of you who aren't familiar with QString, it's pretty similar to stdstring, except it uses Unicode internally. What's important is that it doesn't guarantee null termination, the version that we were using at this time. So here's a piece of code. And we're looping over all the characters in the string. And we're saying, OK, if the next two characters are colons, great. We found a scope. We're going to save the class name. There's a problem with this code. Does anybody see the problem with this code?
Yes.
Absolutely. So
We've
right
gone
here,
beyond the string.
yeah, so on this line, when we access index +1, we have undefined behavior. We're off the end of the string. a smart compiler looks at this and says, aha, this loop has undefined behavior on the last iteration. Therefore, I know that the only way this code can make any sense is if I never hit that condition. How do I make sure there's no last iteration? There must be no iterations. Therefore, the input string is always empty. I'm going to throw out all of this code, and class name is always empty.
This was a pain to debug because we could always see the input string, and every time we went through here, it was empty. And we're decent programmers. This took a while, actually, to find. And looking at the code, you see the error, but you don't realize what's going to happen with the undefined behavior.
On what optimization level do you define?
That's a good question. I don't think we ever
I don't think we changed optimization levels. We have it set at a mid-range to...
Once we found the bug, we just fixed it.
Yeah,
so we didn't experiment to see.
And somebody had mentioned, oh, doesn't this short circuit? That's why we've added this. This was in an older version of CopperSpice that, again, it was not guaranteed to be null terminated. Our new version of QString that is Unicode aware, that wouldn't happen this way. And we've cleaned up the code so it doesn't look like this anymore.
But that can show you just how much compilers can rewrite your code to do strange things when you have undefined behavior you don't see.
We had another problem when we were developing some initial, the initial code of the core part. Once we got rid of mock in Qt and we were running through our initial diagnostics, we were wanting to see what was happening when we were doing our registration. So like everybody else, we threw in a printf. And the printf was using a QString. And we were having a very hard time debugging. So like a good programmer, we kept moving the printf. And the error kept moving, which gave us a hint. We then tried a const character star. It didn't crash. With a QString, it did.
So it turned out that internally, QString used a static data member. And we had the classic static initialization order problem, where it wasn't available during static initialization because that was what we were trying to debug, was our static initialization process. So we had to take that static data member, wrap it as a function local static inside a method, therefore it gets initialized on first use. We're not using an uninitialized variable anymore. Life is good.
So this does address the point that it was uninitialized before, and so we got random stuff at startup.
There's another one that points out how difficult it is to even determine if something is well-defined in the standard. There's a chunk of language in the standard that says relational comparison of pointers is only defined if the pointers point to members of the same object or elements of the same array. So here, I'm comparing the address of two local variables. It doesn't fall in either of those categories. But there's another thing in the standard that says anything which is not defined is undefined behavior. So anything that you missed in the standard that just isn't there results in undefined behavior. However, there's another rule near this first rule that says, but in this particular section, we are saying that any comparison between two pointers which is not defined is actually unspecified.
This was actually kind of loosely worded in the standard. This has actually caused a fix in the standard that's coming out. Yeah, so we've actually caused a cleanup in the standard.
Yeah, there's a defect report a wording change in this area to make it less confusing.
Because it should be unspecified behavior, not undefined. And it took 3 different places over about 10 different pages in the standard.
There's also a very interesting example here. Thanks to Clang for this one. We have a function here that's going to sum the first max numbers. And a sufficiently smart compiler, otherwise known as Clang, can look at this function and rewrite this without the loop using Gauss's formula for the sum of the first n integers. But why is it able to do that? Well, there's a reason. The compiler is allowed to assume you will never call this function with an integer value that causes a numeric overflow. That's really important because if overflow occurs, then the result you get from the formula is different than the result you get from the iterative solution. But since those values aren't valid, the compiler is allowed to make this transformation. And if you play with the constants in here, you'll actually see the formula that it uses change to make sure that the set of numbers maps perfectly to the set that has defined behavior.
This one's kind of interesting and very surprising. If on do thing 7, you see that we're doing we're receiving this as a const reference. We're const casting. So we're taking away the constness. There's a problem here that if when this variable was initially declared, if it was declared without the const, with the const, then you have a problem because you're taking away the constness. So now you could introduce undefined behavior just by playing with const. But what if the initialization is way over here in your code and it's getting called over here? It's impossible to see how it was initially declared.
And this function and the one just previous to it are examples of a really interesting category of functions that cause a lot of errors. These are functions that have undefined behavior for some inputs. And it's really important to document in the API what inputs those are, because there's no way from the outside to know that there's a const cast in this function. There's another one that actually comes up occasionally. Specializing a type trait as undefined behavior, because if it wasn't, you could do this. This makes no sense. I've just specialized isPointer to say int is a pointer type. This is obviously nonsense. It will completely mess up the standard library. And so they just say, this is undefined behavior. You can't ever do this. No compiler will diagnose it, and this is undefined behavior that occurs at compile time. So your entire program is invalid.
So now we start to get to what I find is the more interesting part, is sequencing. So sequencing is the piece that's missing from most talks about undefined behavior. Sequencing is the idea that the behavior of a program depends on the order. I mean, obviously, you've written your program that things happen in a particular sequence. So here we're going to talk about what sequencing is.
This is also really useful to understand if you're doing any multi-threaded programming, because until you can understand how sequencing works within a single thread, it's impossible to reason about the connections between threads.
But before we do sequencing, we have to talk about side effects.
So this is the computer science definition of a side effect. Side effect is what happens when you change the state of your program in some way. You modify a variable.
So there's some definitions. We're giving you everything you need up here. And we want to know how many side effects. So we've got 2 different examples for line 1 and line 2. So given these definitions, that it has a side effect if it modifies some state, such as changing the value. But the following are not considered side effects: returning a value and a statement with both declares and initializes. So now is when everybody gets to participate. How many side effects on line 1?
0.
Does everybody see that? Why it's 0?
Because this addition isn't a side effect. It's not stored anywhere. It's just a value. And assigning to var a is not a side effect because we're putting a new value in a new memory location. So it didn't have a previous value to modify.
So the number of side effects here?
1. Good. Got a good crowd today. So yes, there's exactly 1 side effect here. Because we've split this in 2 lines, we're doing an assignment here, which means there's a side effect occurring. Even though the previous value was uninitialized, this is considered to be a side effect.
So in C++, again, based on the standard, these are the only things which can cause a side effect. Reading a volatile object, write access, calling library I/O, or invoking a function which does one of these things.
And this is a complete list.
Complete list.
These are
This
the
is
4 things which cause side effects in C++. So how many side effects do we have here? 1.
Making an assignment, there was no initialization at the same time.
So we've got 1 side effect here. How about here? I like that. I'm hearing 2. I agree with that. We've got the assignment is one side effect, and the decrement of var A is a second side effect. So why does this matter?
So a sequence point. This is a location in your code, usually at the end of an expression, where these side effects are done and these are kind of waiting to happen.
So the idea of a sequence point is you can point to a place in your program right there. I know that all the previous side effects are finished. I know nothing after it has started.
Sequence points are actually, they were part of C++ and the core language. Even if we didn't really talk about them, they've been there forever.
But not anymore.
Oh, yes. In C++ 11, and sequence points came from C. And they realized there was a lot of definitions that were wrong. So as of 11, the whole idea of a sequence point, this code, this terminology in the standard was completely changed. So now it's sequence before, sequence after. And then it's called sequencing, which is a strange way. I wish they had used a little different word, but they added the ing.
So now instead of looking at a point in your program, we have to be able to ask this question about any two arbitrary expressions in your program. If we look at two expressions, A and B, they can have one of three possible sequencing relationships. A can be sequenced before B, which is the same as saying B is sequenced after A. Those translate to each other. Or A and B can be indeterminately sequenced, which means the compiler must do one of them first and one of them second, but it's free to reorder them. Or they can be unsequenced, which means there's no restriction. The compiler is allowed to interleave or overlap the processing of those expressions.
So here's another example. We have example A and B. The question we're asking is, are any of these undefined behavior?
And this sentence from the standard is the most important sentence in this entire talk. There are many that are very useful. This is the key. If two side effects, or a side effect and a read, occur on the same object, and they are unsequenced, you have undefined behavior. That's the connection between sequencing and undefined behavior.
Any thoughts? Is it undefined? Does anybody think this one's defined?
What about this one?
Why?
Right. Shall we find out? And the survey says?
And the survey says?
It depends.
It depends. In 03, C++ 03 was all undefined.
Because in 03, there was one sequence point at the semicolon.
Yeah.
You're done.
In C++ 11, they made this one defined because of it's a pre-increment. They kind of made a mistake, and they forgot to do post-increment until 17.
So before 17, there aren't enough rules in the standard about sequencing to force a sequence on this whole expression that actually produces defined behavior.
We forgot to kind of add this isn't necessarily beautiful code. We don't necessarily advocate code like this. We're changing var B on both sides. So you might want to maybe not do this code. But to really show a real-world example takes a lot of space. So these get the point across. Okay?
Another one that comes up quite frequently is the order of evaluation of the things you're passing to a function. And it was originally unspecified. So it could be anything. They changed it to indeterminately sequenced in C++ 17. And this is useful because it made a lot of things defined that weren't. There's still an interesting thing. It's still a really bad idea to have side effects in your function arguments. And the reason is this. We're assigning to var1 in the first argument to this function. And we're passing var1 in the second argument. Now, before 17, this is just complete garbage, totally undefined, because those two expressions are unsequenced. So you're done. In 17, the compiler is allowed to choose either one of these orders. It has to evaluate both arguments before it actually calls planned dinner. That's required. If it picks this option, then the behavior is well defined. If it picks this option, you're using var1 before it's initialized.
And
That's undefined behavior.
And it doesn't matter if it's an evil compiler or an efficient compiler. There's no way to know. This is not something you can predict because it's indeterminately sequenced. You can't ask the compiler, could you do it the good way?
Now you may say, I would never write code like this. Have you ever allocated memory in an argument list? You have written code like this. If it's not wrapped properly with something like std make unique or things like that, you have weird and subtle ordering bugs in undefined behavior, almost certainly.
No,
Yeah.
it is indeterminately specified, so that could be undefined behavior.
So this is sort of a weird state because the compiler has the option to interpret it as undefined behavior. Therefore, it is undefined behavior.
But it's based on the indeterminate, so you kind of end up in undefined if it does the second one. I know this wasn't pleasant. So here's another example. We're going to look at what result. We've made sure the math is very simple, fingers work. So we have var b is equal to 4. I guarantee one of these is the answer. It may be the boot sector. So what we're trying to figure out in this example is what is the result and where is it stored? And we have plenty of time. Look at that,
wonderful.
Plenty of time to do this.
So, would anybody hazard a guess as to which one of these options they think is most likely to be the result? People catch on quickly here.
We're just not as sneaky as we used to be. Based on which standard?
That's an excellent question.
Based on, so pick a standard, pick an answer. Oh, so we have a vote for number 1.
Okay. So, assuming some standard where this is defined, and we won't talk about which one at this point, what result do you think we should get?
We've got the first one. Anyone for this one? Cool. How about this one? Don't be shy. Nobody's voting for that one. This one? I like the boot sector. Is anyone completely unsure of how to work this out? We're going to walk through it. You're completely unsure. Cool.
All right.
Do you want to guess before we show you some of it? No, you don't want to guess. It's okay. We don't either. Okay, let's start looking at it.
So,
There's undefined in 11.
and this is the standard language, except slightly edited for clarity. There's a rule that says the value computations, but not the side effects, of the operands to any operator are sequenced before the value computation, but not the side effects of that operator. And what this is saying is in order to do the assignment, we have to compute the left-hand side and the right-hand side, certainly. That has to happen before the assignment occurs. However, we don't have to finish the side effects of both sides. So the order of evaluation of the values is sequenced, but not their side effects. Now I said this was edited for clarity. The edit is, I put in the phrase, but not the side effects. It doesn't say that in the standard. You have to know that if it says the value computations and doesn't say the word and the side effects, it's not talking about the side effects. So these rules are very difficult to read because there are two different things which you're looking at, the values and the side effects, and they're not always obvious which one the standard's talking about.
Did we lose anyone? Cool. No questions? This makes sense how complicated this is. And that code that looks like that, which isn't great code, but I'm sure people have done it, it is actually undefined in 11.
So let's get in our time machine and go forward.
It's defined in 17. And the way the math works on here is we're going to take the 4 and the 3. We're going to get 7, 4, 5, 6, 7. That works.
Then there's a rule in the standard that says in 17, all of the side effects on the right side of the assignment operator must be complete before evaluating the left side. So at that point, we've got the value 7, just holding that. Now we increment var b to 5. Now we can go to the left side. Now we have a new rule that says in the subscript expression, the thing on the outside of the subscript must be evaluated completely before the inside. And this turns out to be enough to force us to evaluate this post increment before we compute which index element is being used. Now it's post increment, so we can compute this. We've looked at my array. We get element 5 because that's the current value of var b, and then we increment it to 6. So the end result, if we pop back to here, it was this one. We ended up storing the value 4 plus 3 in element 5 because only one of the increments, exactly one of the increments had occurred by the time we evaluated this part of the expression.
So var b does get incremented, but in some ways it may just get thrown out. But it's very important to know that var b is going to become 6, even though it's saved to array element 5. Interesting?
We were trying to prepare for this talk and figure out which one of these things were actually well defined.
It turns out that, and these are the ones we've looked at, is GCC 7 and 8 and Clang 6 and 7. They still report much of this as a warning, which doesn't make sense because things that are defined in 17, and if you're using 17, shouldn't be a warning. But they still report it as a warning just to let you know if you decide to use an older compiler, it might be undefined.
Now, technically, GCC's message is correct here because it says operation of var b may be undefined. Clang is more sure of itself and is actually wrong.
Yes. This is an actual quote that we found from GCC trying to say we're still just not sure what's going on.
So if you turn on warnings about undefined behavior and sequencing, and you're going to use the 17 sequencing rules, you have to filter for false positives, which is unfortunate. And you can take examples from CPP reference and plug them into current compilers, and you'll see this happen. They're well-defined examples, but you'll get warnings on them.
So we just wanted to also throw in the idea. Flat map is actually coming to C++. We needed it in CopperSpice, so we added it. The reason why we wanted to throw this in here is it is undocumented behavior. There is no flat map in the standard. So now, just like in any class that you have, you're adding functionality. It isn't in the standard, so shouldn't that be undefined? No, because there are actual rules and things in the standard that say you can add classes. The nice thing that we did is, and a flat map is just the combination of a vector and a map. So this is undocumented behavior, just another piece of terminology. What's important is that since we're adding new functionality, as library developers or as people developing various classes in your stuff, you want to make sure you hit the abstraction right so that you're actually developing something which speaks to the class that you're adding. It would be ridiculous for us to have done a flat map that was a set or just something that didn't make any sense.
Then there's the rules about undocumented, undefined behavior. And there's a rule in the standard that says anything which is not explicitly defined in the standard is undefined behavior. So if you go through your entire program, nobody does this, but if you go through your entire program and find the rule that each one of your lines uses, if you can't find a rule, your program has undefined behavior. And this can be challenging because how can you find a rule that isn't there in the standard?
So one of the questions then is, if I can't go on Godbolt and ask it if this is undefined, how do I know I'm undefined or I'm defined? It's tricky. We unfortunately can't give you a one rule fits all because we're saying, don't do this, but we can't tell you how.
So there's a lot of stuff you can do in code reviews. And you really should educate your whole team about how important it is to look for undefined behavior in every single commit, because one bad commit will ruin your entire project. You should try with different compilers, different optimization flags, see if you can provoke some unusual behavior. This is really important. If you discover undefined behavior, it is a P0 bug. It doesn't matter if it's rare. It doesn't matter if you think you can't get to that code. You need to fix it immediately.
We had somebody that was chatting with us and said, I was running my unit tests, and some of my unit tests now pass, and yet I have undefined behavior. And he was very confused on I think I have undefined behavior, but my unit tests look great.
The answer is, unfortunately, if you have undefined behavior, your unit tests don't tell you anything, because the pass that it prints is after your program has encountered undefined behavior, so it's in an unknown state. The compiler might simply say, well, I'm pretty sure all of that code is undefined behavior, so I'm not going to run any of it and just tell you it's fine. There are also static analysis tools that you can use that are very useful. They will find certain classes of undefined behavior. Some of these are commercial, some of them are open source. Try them out. Sometimes there are some false positives, and sometimes the output can be too complex to really reason through, but they're useful. The runtime sanitizers are the ones which are particularly useful. And the Clang suite of sanitizers have been designed in such a way that there are no false positives. If they find and report an error, you have undefined behavior in your code. You can bet on it.
Yes.
Good question and good comment. The comment was thread sanitizer is an exception to that. It is. However, I have proved to my satisfaction that something was a false positive and been wrong. So it's right more often than your intuition about the code is. But yes, you're correct. That it sometimes can be a false positive. These are fantastic because they catch a lot of common categories of errors. They can't catch everything because the list of what is undefined behavior is an infinite set.
So we just wanted to let you know that we do have a YouTube channel. We hope you'll subscribe to it. We've actually recorded undefined behavior. We had a new release yesterday of a video. We do these now once a month. They range from about 10 minutes to 20 minutes. It depends on how long we feel like talking. But we hope that you subscribe and check out the videos. If you don't know what CopperSpice is and DoxyPress and what we're doing, that's some of the early stuff. We have 3 videos on data types. If you're any doubt about data types, it's a great review. Really starts covering a lot of all the stuff that came in. Const expert, static const is just a lot of fun to say. And again, we have CopperSpice and a bunch of libraries. Everything we do is open source. Everything's on GitHub. We give everything away. How do we make money? No, I'm just kidding. If you're not sure what CopperSpice is, you're not sure what a GUI library is, Kitchen Sink is a demo program that has about 30 different demos. It's not optimized, it's not pretty, but it shows all the different widgets and controls. And this is how to find us. We have source available and a small discussion group, and wow, we made it with 6 seconds to spare. So that's what we have. Thank you very much.
Thank you too.